All right, I am now recording, and I wanted to show you something first. I've redone the formula sheet for the oscillations, waves, and sound section, which is tomorrow's test. And I'll post this as a PDF right after class, and you'll be able to print this off and practice with it, get familiar. Tomorrow for the test, you'll get a fresh copy of this, and we'll work that out somehow anyway. But I've got a section on simple harmonic motion, a little section on the simple pendulum, and then introducing traveling waves with some of their formulas, the speed on a stretched string, superposition of waves. I should have had that little heading above it maybe. Standing waves on strings, what those will look like, and the frequencies that can exist for standing waves on a stretched string. And then a section on sound waves, including those things that the displacement amplitude and pressure amplitude, although I tend not to ask questions about this on the test, so don't worry about that too much. There's plenty of other stuff to concentrate on. Anyway, the intensity of a wave, and how it depends on pressure amplitude or displacement amplitude, and then air density. So these would be for if you'd had a homework problem on that stuff. But then I've got the sphere surface area. You might relate that to the power and intensity. So we might do something with that. Sound intensity level, decibels in other words. Sections on wave interference and introducing the idea of a path length difference and then the phase difference that arises because of that path length difference. Just a sec, I have to shut a door. Constructive and destructive interference, what the requirements for a phase difference for those two considerations, and then just the beat formula, and then the Doppler effect for sound. It's probably too small for you to read on here, but it's on there anyway. And then I just mentioned the speed of sound, 344 meters per second at 21 degrees Celsius. And any problem where you're not given the speed of sound, but you need it. Oops, I need to drag something down. Looks like that got cut off a little bit. But just assume the speed of sound is 344 meters per second. And then I've got the formulas for standing waves in pipes, which these aren't presented in the order that we studied them in, but I just happened to, I don't know, juggled some stuff around so I could make everything fit. And then metric prefixes at the very end. So just in case you might need those. So that's what we have going so far. Last Thursday introduced gravitation for the first time. And all we did last Thursday was look at some problems involving the gravitational force. Today, I want to look at energy for gravitation, gravitational potential energy in particular. And what I'm going to do for introducing that is think of the idea of work done by gravity and done by the gravitational force. Okay, that's supposed to be a V there. Anyway, and that's what it is. Okay, because fall quarter, when we studied gravity, we just assumed the work done by gravity would just be mgh, where g was the acceleration due to gravity, m was the mass of the thing, and that's what we had, but that only works close to Earth and close to Earth's surface, that is. And that work would be minus mg delta y, or that would be the work done by gravity. When we defined potential energy, we thought of it as the work we would have to do to lift something up in Earth's gravitational field. And so we didn't look at the work done by gravity. We looked at the work we would have to do against it. Well, that works as long as G is constant. But as we found out last week, the force gets weaker with distance. It's G times the mass of the Earth times the mass of whatever object it happens to be, divided by R squared. If we're sitting on the surface of the Earth, we can replace the lowercase r with the radius of the Earth. But you can see this force gets weaker with distance from the center. And so we're going to have to take that into account. So now let's think about the work done by the gravitational force as we move larger distances away from the Earth. And so we'll just think of this. Well, I'll write it out. Work done by gravity, and then we'll find out what that work is and flip it, change its sign to make the work we would have to do against gravity to lift that object up. So anyway, work done by gravity as an object moves from R sub A to a higher R sub B. And we're going to be considering much higher things, like we may be putting satellites in orbit. Okay. Well, you put a satellite in orbit and the acceleration due to gravity at a low Earth orbit point is only about 88%. Well, only. It's not that much difference. It's about 88% of what it is on the surface, but we can't use mg delta y anymore with that big of a change. And then if we put something into something like a geosynchronous orbit, the gravitational force out there where the geosynchronous orbit is, and we'll learn what that happens to be, but it's less than 4% of what it is on the Earth's surface. And so we need to have a better expression than this. And it's pretty easy to get because you know how to do integration now. So here's the idea. We'll look at the work done, which in this case, we're not going to be able to just write F delta X. We're going to have an expression that has the force, and we're going to be going up in distance. And I have to take into account the fact that we're going in the positive R direction. The force points downward in the negative R direction. And what this ends up being, it's going to be minus the integral as we go from R sub A to R sub B. This is the beginning point. This is the ending point of the force, the magnitude of the force now, which is going to be G times the mass of the Earth times the mass of the thing that we're moving up there, divided by R squared. There's the force. And then we just have the dr tagged on there. Well, as you've learned in calculus, if you've got a constant, it can come outside of the integral. And so this work is going to equal minus G times the mass of the Earth times the mass of the thing we're lifting up. And then we've got the integral R sub A to R sub B. And left inside is just dr over R squared. Well, shoot, that's an integral you probably know how to do, at least I hope. If not, you will soon. And hang on to this. I still have minus g times the mass of the Earth times the mass of the thing there. When I do this integral, it evaluates to minus 1 over r. And if you took the derivative of minus 1 over r, you would get 1 over r squared. And then I have to evaluate that at r sub a and r sub b. I'm not positive in the notation in calculus anymore. Maybe I should close this parentheses or whatever, but or close it there. I don't know. Anyway, I've got a minus and a minus. That gives me a plus. And so that work is going to equal G times M sub E times M. And when I evaluate this at those 2 points, this would be a plus 1 over R evaluated at these. I'd get 1 over R sub B minus 1 over R sub A, or distributing this through, I'd get G times the mass of the Earth times the mass of the thingy divided by R sub B minus G times the mass of the Earth times the mass of the thingy over R sub A. And you look at that and you think, well, wait a second. We moved the object up. Gravity's acting down opposite. Shouldn't we end up with a negative result? Well, think about these. I said that RB was higher than RA. That means for this term, I'll have a smaller number on the denominator than I do on this term, which means this term is larger than that term, and I'm subtracting it away. So this is negative. Now, that's the work done by gravity. If I think of the work I would have to do against gravity, it'll be the opposite of this. And let me show you what that will look like. I can think of that as the change in potential energy, the work that I would have to do against it. And I would call that the potential energy of R sub B minus the potential energy of R sub A. That's the work I'd have to do against gravity. And it's going to equal the negative of this. Well, I just swap these things. It'd be G M sub E times the mass of the thingy over R sub A minus G times the mass of the Earth times the mass of the thingy over R sub B. So this is the change in gravitational potential energy as we lift the thing from R sub A up to R sub B. Well, that's okay, although sometimes we might want to just be able to define gravitational potential energy relative to something. In this system, we want to be able to just say what it is at some point. Well, here's what we do. We let R sub B go to infinity, and we're going to define the gravitational potential energy at infinity to equal 0. That's our choice. We can pick it anywhere we want, but it doesn't make sense to put it on the surface of the Earth anymore because we're going to be moving things all over the place, and they may not even start from the surface of the Earth. And then we'd like to extend this to gravitational potential energy with respect to the sun or with respect to some other planet. And so here's what we do. We'll let U of infinity equal 0. Okay, so that's what it'll be when you get infinitely far away. And anywhere short of that, you're in a hole that you have to get out of. And we'll just let R sub B equal infinity. Well, if R sub B is infinity, this term vanishes. It goes away. And this, I defined it to be 0. So I'll have minus U of R sub A is equal to g times the mass of the Earth times the mass of the thing over r sub a. Or multiply both sides by -1, and I get u of r sub a is equal to minus g times the mass of the Earth times the mass of the thingy over r sub a. And I just picked r sub a arbitrarily. It could have been anything. So let's just replace it with r. And here's gravitational potential energy now. U of r is minus g m sub b m over r. Okay, I can make a graph of that. And so this will be u of r. Here's 0. Minus is going in this direction. If I graphed 1 over r, or actually minus 1 over r, here's what I get. I get something that looks like this. And what I find out is, as I get very close to the center of the object, now there's a limit when you're talking about the center of the Earth. You can't get past the surface of the Earth. And so that part just doesn't mean anything. But as you go up there, you're climbing out of this potential energy hole and getting closer and closer to 0 as you go to infinity. But that's the best you could do, is to reach the 0 of gravitational potential energy. I think I've mentioned before this science fiction series that I read all the books for, and then it was on Amazon, a show called The Expanse. And in the books, they refer to, if they go down to the surface of the Earth, they refer to it as going down the well. And then when they come back into orbit, they have to climb out of the well. And that's one of the first books that I've ever read where they actually referred to that and talked about the gravitational potential energy. But that's the way gravitational potential energy is going to look for us. So let's see what we can do with that anyway. Well, one of the first things we can do with that is imagine that we have something on the surface of the Earth, an object is launched. From Earth's surface with just enough speed to escape Earth's gravity. Now, what we mean by that is that means that object can go out to infinity. Okay. Now, when it gets to infinity, which is a non-existent place, but when it gets there, it's just barely going to be moving. And so, or it may reach infinity and have a speed of 0 when it finally gets there. So all the way out, it'll be increasing in gravitational potential energy up to 0, but slowing down gradually. And so how fast does it have to be going? Well, let's look at the initial situation. At the initial situation, its energy will be minus g times the mass of the Earth times the mass of the object divided by, in this case, the radius of the Earth. Okay, that's its initial point. It's on the surface of the Earth. But we give it some kinetic energy there, and I'm going to call that kinetic energy 1/2 m v sub e squared, where v sub e is the escape speed. So there's our initial energy. What do we have in the final situation? Well, we've reached infinity, so there's no gravitational potential energy And at that point, it will have slowed down to where it has no kinetic energy either. So what we have is zero for the total energy. Now remember, energy is just a bookkeeping system. We can define zeros for it to be whatever we want them to be, and we chose it to be zero at infinity for this. Excuse me. And the kinetic energy will equal zero out there as well, because it'll have stopped with respect to the Earth out there. Well, let's just solve for V sub E. Okay, kick that term across, divide both sides by m, and I'd get 1/2 V sub E squared is going to be G m sub E over R sub E. Multiply both sides by 2 and take the square root, and we'll get the escape speed is going to be the square root of 2G m sub E over the radius of the Earth. Well, we can calculate that. Let's do it. V sub E, escape speed from Earth, is going to equal the square root of 2. Remember, G is 6.67 times 10 to the minus 11. Newton meters squared per kilogram squared. And then the mass of the Earth. Oh man, let's see. I need to look that up because I think it's 5.97 times 10 to the 24th kilograms, but I could be wrong. And so I'll just pull the book out here, and actually are these, no, they're not. Maybe they are. Yes, astronomical data. Earth. Mass, yes, 5.97 times 10 to the 24th times 10 to the 24th kilograms. And then the radius of the Earth, I think, is 6.37 times 38. 6.38 times 10 to the 6 meters. So meters, where'd that come from? Oh, that's part of a G. All right. All right. Well, what are we going to get for units? Kilogram here, kilogram there, kilogram squared there, meter here, meter there. I'll have Newton meters per kilograms underneath. But a Newton is a kilogram meter per second squared, and I'll be multiplying that by meters over kilograms, and kilograms divide out, and I'll have meters squared per second squared under a radical, which when I take the square root are meters per second. So what I get for escape speed is, where did I put my calculator? Buried. Just an arithmetic problem at this point. And I get about, let's see, I had 3 sig figs on things. I would get 1.12 times 10 to the 4th meters per second, which is the way you see that this often written is as 11.2 kilometers per second. You take 3 off the exponent and make that a k, and you'll have 1.12 times 10 to the 1. So anyway, 11.2 kilometers per second. That's how you get off the Earth. Now, with that speed, ignoring air resistance, because you have to overcome a lot to get out of the atmosphere. But anyway, it'll just reach way out there. and barely be moving. If that's all the faster it's going, well, you might have to be patient, but just give it more speed than that, and it'll easily escape Earth's gravity in effect and still be going at a pretty good clip. So if you multiplied this by 50%, say, you'd get there with I don't know, fair amount of speed still. In fact, you could figure that out if you put factors in front of this thing. If you wanted to be going at, say, 10% of the escape speed when you get out to infinity, you could figure that out. So, all right, there's our first little problem that we've done with escape speed. I've got a bunch more here, and I'll post these after class as well. Here's one. Is it possible for a planet to have the same surface gravity as the Earth, that is, the same value of g at the surface, and yet have a greater escape speed? Well, let's take a look at it. What we got for escape speed, V sub E, was the square root of 2 times g times the mass of the Earth over the radius of the Earth. Okay. Now, acceleration due to gravity on the Earth's surface, we can get that from on the Earth's surface, the force on something, the weight, is mg, but it's also equal to g times the mass of the Earth times the mass of the thingy divided by the radius of the Earth squared, or if you divide both sides of this by little m, you get that the acceleration due to gravity is g times the mass of the Earth over the radius of the Earth squared. Now, wondering, some other place has the same acceleration, same surface gravity as the Earth does. What does that mean? That means this ratio is the same as that for the Earth. But there are other ways to get this ratio to be the same. You can have more mass and a larger radius and still have the same acceleration due to gravity. You can have less mass and a smaller radius and still have the same acceleration due to gravity. But would this planet necessarily have a greater escape speed? Well, those are the physical factors that are going to determine the escape speed. It's not the mass over the radius squared anymore. It's just the mass over the radius. So it should be possible for this number for that planet to be bigger than it is for the Earth, and this number for that planet to be the same. So let's say that we'll call this planet X. The mass of X over the radius of X. Let's just assume that it's equal to, or it's greater than, the mass of the Earth over the radius of the Earth. But at the same time, we have that the mass of X over the radius of X squared is equal to the mass of the Earth over the radius of the Earth squared. Well, how's that going to work? These two are equal here, right? What if I multiply both sides by r sub x? Okay. So I have mx over r sub x squared times r sub x equaling r sub x times the mass of the Earth over the radius of the Earth squared. Okay, those two are equal. These are not. So I'd get mx over r sub x is going to equal, well, what I've got is the mass of the Earth over the radius of the Earth. I'm going to break this up a bit, times r sub x over r sub e. This is the same as this. And the way you can do it, the way you can make this greater than that is just to have, this is going to be a dimensionless quantity, but you just have the radius be bigger than the radius of the Earth. And that way you can have, this still has to be an equality, but it'll make that be the same. Let's see, is that correct? Yeah, as long as the radius of planet X is bigger. You'd also have to have a larger mass for planet X, but it's spread out in such a way that that's the case. So you can do it. Okay, let's look at another situation there. The asteroid Dactyl, discovered in 1993, has a radius of only about 700 meters and a mass of 3.6 times 10 to the 12th kilograms. We'll learn shortly, especially in tomorrow's lab, just how you can determine the mass of something, even though you can't get anywhere near it. Probably Dactyl has a companion asteroid that orbits around it, and by studying that orbit, you can determine its mass. Or maybe we've flown a spacecraft past it. That's another way. You look at the effect the gravity of this thing would have on the spacecraft, and you can figure out its mass. So calculate the escape speed for an object at the surface of Dactyl. Well, we'll call that V sub D, or maybe VE comma D, okay, for the escape speed from Dactyl. It'll be the square root of 2 times G times the mass of Dactyl divided by the radius of Dactyl. And we just plug in the numbers. Now, we already know they'll come out meters per second, so I don't have to sweat that anymore. But 2 times 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared times mass of Dactyls 3.6, not much compared to the Earth that 10 to the 24th, 6 times 10 to the 24th, but 3.6 times 10 to the 12th kilograms. And then let's see, the radius, 700 meters. Okay, escape speed from Dactyl will be, plug and chug. And I get about 0.8 meters per second. Okay, well, you can walk that fast. And so presumably you could reach that speed just by walking, except something you depend on for walking is friction, a frictional force between you and the ground. So you can not have your feet slide backwards on you. And this is not very much. And so the gravity there is going to be a tiny fraction of Earth's gravity, and there isn't going to be much friction. Now, whether or not you could jump off of Dactyl, I've never bothered to calculate the speed as you leave the ground for particular jumps, but you could try to figure that out for yourself. Suppose you can jump to a height of 0.2 meters or something like that, or maybe 0.3 meters. Actually, that's only that far. Should be able to jump that far. How fast are you going when you leave the Earth's surface in that case? Okay, well, you could easily do that on Dactyl just by bending your knees, squatting, and then straightening your legs and find out how fast you can be going leaving the surface of Dactyl. And if that's how fast it, or if you can jump with an upward speed of greater than that, you will leave that asteroid and not come back. So you'd have to be careful walking around on Dactyl, possibly. Actually, we can do that calculation real quick. Let's suppose we'll just look at a gravitational potential energy on Earth. So you'd have 1/2 mv squared plus equals mgh. Now I can use this because I'm going to be near the surface of the Earth, and the v squared will equal 2gh. V will equal the square root of 2gh. And we can figure out, let's suppose you can jump 3/10 of a meter. What would your speed be coming off the ground? So I'll just plug in 2 times g times 0.3 meters and see what we get. Square root of that is. Okay, yep, you can jump off that thing. This would be 2.4 meters per second, which is 3 times as fast as you need to escape from Dactyl. And that's the speed coming off the ground on Earth if you're jumping that high on Earth. So if you left the ground on Dactyl with that speed, you'd leave and not come back. So got to be careful if you're walking around on that thing. Okay. When in orbit, a communication satellite attracts the Earth with a force of 19 kilonewtons. Now, that's the force that the satellite exerts on the Earth, but it's also the force that the Earth exerts on the satellite, because Newton's third law controls or always works. And the Earth's gravitational potential energy relative to 0 at infinite separation is minus 1.39 times 10 to the 11th joules. So find the altitude of the satellite above the Earth's surface and find the mass of the satellite. Well, I guess I can actually use either one of these things to figure this out, I think. Gravitational potential energy relative to 0 at infinite separation. Well, that looks like G is going to be minus capital G times the mass of the Earth times the mass of the satellite over R. Oh, this would be U sub G. And what we don't know is the distance of its orbit or distance from the Earth's center. That'll give us that. And then if we subtract off the radius of the Earth, we'll have the altitude above the Earth's surface. So we ought to be able to do that. And they give us this number. It's minus 1.39 times 10 to the 11th joules. Okay, well, the only thing we don't know here is R. So R will equal, oh, we don't know the mass of the satellite, right? So we may have to do a little bit more work, but let's just see what we can do. Oh, we also know it attracts the Earth with a force of 19.0 kilonewtons. Well, that force is going to be G times the mass of the Earth times the mass of the satellite over the radius. Actually, it'll be over this R squared is what it's going to be. But I think that may be a way to figure out R. Because if I look at, oh, they give me the value of that 19.0 times 10 to the 3 newtons. That's kilonewtons. So I have that. What if I take the absolute value of the gravitational energy and divide it by that force? What would I have? I'd have G m sub E m over whatever that radius is divided by G m sub E m over R squared. And what this ends up equaling is just R. The G m sub E m's divide out. 1 over R divided by 1 over R squared is just R. So I just have to take the ratio of the absolute value of this divided by that. And R, we'll find out the mass in a second here. R is going to equal 1.39 times 10 to the 11th. A joule is a Newton meter. And I'm dividing by 19.0 times 10 to the third, just plain newtons. So I'll end up, that's a 19, end up with meters. And we can find out what it is here. And I get 7.32 times 10 to the 6th meters. Okay, now that radius is going to equal the radius of the Earth plus the altitude above the surface. And so the altitude above the surface, I just subtract that off. So H is going to be 7.32 times 10 to the 6th meters minus, oops, I closed the book. Oh, it was in the back cover though. Radius of the Earth, again, the copy of the book I have is that 6.38 times 10 to the 6th. So 6.38 times 10 to the 6 meters. Oh, my wife's hollering at the puppy we just got. So it'll be, let's see, 7.32 minus 6.38. I think that's 0.94 maybe, but I'll check it. Yeah, it's 0.94 times 10 to the 6th meters, or 94 times 10 to the 5th meters anyway. So that would be the altitude above the Earth's surface, which should be, let's see, 9.4 times 10 to the 6th. That'd be 9,400 kilometers. So yeah, something like that anyway. So more fun. Okay, 10 days after it was launched toward Mars in December 1998, the Mars Climate Orbiter spacecraft, with a mass of that, not much, 629 kilograms. That's about half the mass of a small car, actually. But it was that far from Earth and traveling at 1.20 times 10 to the fourth kilometers per hour relative to Earth. And we'd like to know the spacecraft's kinetic energy relative to the Earth. Well, that's just going to be, KE is just going to be 1/2 mv squared, where v is its speed relative to the Earth. Kinetic energy is a relative thing. It depends on what you're measuring it with respect to, the speed or the velocity with respect to. So that part's not bad. So 1/2 times 629 kilograms. I don't remember. Actually, I'm going to do a quick Google search on this thing. That may be a spacecraft we lost. Yeah, let's see. Yep, that was the one that let's see. Yeah, anyway, let's go ahead and calculate the speed and then I'll tell you. 1.20. Now, 10 to the fourth kilometers per hour replaced. Oh, shoot. I need to convert a lot on that. 1.20 times 10 to the fourth kilometers per hour times 1 hour over 3,600 seconds times 10 to the third meters per kilometer. So this is actually 1.20 times 10 to the seventh meters per hour. Okay, we can do that. Then I get 3.33 times 10 to the third meters per second. So that's its speed. Squared. And I get 3.49 times 10 to the ninth joules. So that's what we'll have. Okay. And then, let's see. Oh, we know how far away it is. So now it says 2.87 times 10 to the 6 kilometers from Earth. We're not told whether that's from the center of the Earth or from the surface of the Earth. So although 2.87 times 10 to the 6 kilometers, Earth's radius is about 6.37 times 10 to the, or 6.38 times 10 to the third kilometers. So this is 1,000 times that much, not quite 1,000 times that much, but it's not going to matter if it's relative to the center or matter relative to the surface. Okay, we can calculate the potential energy of this Earth spacecraft system, and that will be U grav at that point is minus g times the mass of the Earth times the mass of the spacecraft divided by the distance it is from the center of the Earth. So we just take this and convert it to meters. So we can figure out how far in the hole it happens to be. So 6.67 times 10 to the minus 11th. let's see, Newton meter squared per kilogram squared. I was thinking the next step up and forgetting about the units of it. Mass of the Earth. We've already done that on one problem, but I need to track it down again. Great. I don't know where I put that. Okay, well, looking at the book again. 5.97. Yes, 5.97 times 10 to the 24th. And then times that 629 kilograms. And then we divide it by the distance away it is. 2.7 times 10 to the 6th kilometers, but I'm going to replace K with times 10 to the 3rd. So you can see it's going to be 2.87 times 10 to the 9th meters. And we'll find out if this number is bigger in magnitude than that number. It's not going to escape Earth's gravity, but I bet this one's bigger. We'll find out. Anyway. Okay. And U grav at that point, grav is minus 8.73. We can keep 3 sig figs times 10 to the 7th joules. So this number is about 4 times as high, or 40 times as high as that number. And so it has enough speed to escape the Earth system and reach Mars. So here's the final story about this thing. When this thing was supposed to go into orbit around Mars, it reached Mars, but it was going too fast. And so they have to have a rocket burn when it gets to Mars to slow it down so it can go into orbit around it. Okay, you aim the rocket in the direction the thing's going and use it to brake the spacecraft, B-R-A-K-E, the spacecraft. Okay, well, when NASA sent out the contract for this thing to be built, and the company that made it, I'm pretty sure was Lockheed Martin, but I'm not 100% positive about that. Anyway, when they put out that contract, they had specified that units for all quantities had to be in the metric system. And so they got the spacecraft back, got the blueprints back, and when somebody went to calculate how long they would have to fire the rocket for, they looked through the blueprints and found this number for the thrust of the braking rocket. And I have no idea what the number was, but it said some number, but it didn't have units by it. Now, they'd said that everything had to be in metric units, and so they assumed that the units that they had on there, the person at NASA did, assumed that they were kilonewtons just by the magnitude of the number. And then let's suppose that it was 12,000 kilonewtons was what the thing happened to be. Turns out, whoever wrote that number on the blueprint had actually written a number in kilopounds. So let's go ahead and see how many kilopounds LB, and I multiply by 4.448 newtons per pound. Then I get something like, well, we don't need that many sig figs. It'd be something like 53,000 kilonewtons, right? Well, they calculated how long that burn, this breaking burn, would have to be, or if this had been 12,000 kilonewtons, but it was actually 50,000 kilonewtons or something. At any rate, they fired the rocket 4.448 times too long. It slowed the rocket down too much, and basically the spacecraft, instead of orbiting Mars, fell into Mars' atmosphere and burned up, probably on the way down somehow. Anyway, that was about a $275 million mistake, which is that when I first heard about that and started talking about it in classes, I would tell my students that, that's almost as much as the advertising budget for the Super Bowl. Now it's well short of the advertising budget for the Super Bowl, but um, it was expensive anyway. Kind of a waste of stuff. Okay, we got another one. We haven't really done much with orbits yet, but satellite in low Earth orbit has an altitude above the surface of 380 kilometers. Actually, let's go ahead and skip this problem. We'll start studying orbits and a little bit later. Shortly after launch, the New Horizons spacecraft had a speed of about 58,000 kilometers per hour. Now, what was that one we just did? This was the Mars Climate Orbiter. This would be about 12,000 kilometers per hour. This one is 58,000 or almost 59,000 kilometers per hour. This one was going a lot faster. I'm pretty sure the New Horizons was the fastest spacecraft we've ever launched from Earth. At the time it was. I don't know if we've done anything faster yet. And the reason for that was this thing, they wanted to get out to Pluto, and it did go by Pluto. That's where our pictures came from. And at that time, was its speed great enough to escape Earth's gravity? Well, how many kilometers per second is that? Let's figure that out. Take 58,536 kilometers per hour and multiply by 1 hour over 3,600 seconds. Okay. Remember, we need 11.2 kilometers per second to escape the Earth's surface, and this was above the Earth's surface. But anyway, will it be enough? 5, 8, 5, 6. Yeah, this is actually 16.2 kilometers per second. So yes, its speed was great enough to escape Earth's gravity. At that time, was its speed great enough to escape the sun's gravity? Huh. Well, now we've actually got two potential energy holes that we have to get out of. One of them is the Earth's gravity, which unfortunately we don't know how far above Earth's surface it was at this time. But let's just put it back on the surface and say that it's U grav total would equal minus G times the mass of the Earth times the mass of the satellite divided by let's see, we'll just call it the radius of the Earth. And then the sun's gravitational potential energy hole is minus G m sub s, the mass of the sun, times the mass of the satellite. And what we would divide that by is the radius of the Earth's orbit. Radius of EO, for the radius of the Earth's orbit, which happens to be 93 million miles or 150 million kilometers. And so that's its gravitational potential energy. What's the escape speed from the solar system if you're starting from the surface of the Earth? Well, we'd want to have these energies minus G, mass of the Earth, mass of the satellite over the radius of the Earth. We've got this other hole that we're getting out of, G times the mass of the sun, mass of the satellite, or whatever it is, radius of the Earth's orbit. And then we're going to give it some kinetic energy, 1/2 mv squared. And when it gets to infinity, it can stop. We just want to get it out of here. Well, we've got little m's everywhere, and we'll end up with the escape speed in this case. I'll factor out, well, I can't factor out much. I'll have the square root of, kick those across, I'll have a 2. I'd have 2 times g times the mass of the Earth over the radius of the Earth, plus 2 times g times the mass of the sun over the radius of the Earth's orbit. And that's the speed we have to have. Oh, I can do a little bit of work in there. V is going to equal the square root of 2 capital G times mass of the Earth over radius of the Earth plus mass of the sun over the radius of the Earth's orbit. Okay, so that breaks down a little bit. I'm just curious what the escape speed is from there. And then we'll stop for today. Times times, okay, mass of the Earth, 5.97 E24. Sorry, I'm not writing all these down. Oh, mass of the sun is about 1.99 times 10 to the 30th, I think. And the radius of the Earth orbit is 1.5, 150 million, 1.5 times 10 to the 8th, 1.5 times 10 to the 11th meters. Whoops, 10 to the 11th. Okay, and for that I get 43,500 kilometers per, or meters per second, which is 43.5 kilometers per second. Don't quite have enough speed to do it. Okay, so at least if I plug my numbers in right. Now, somehow that thing is escaping the Earth's or the solar system. So the way that it did it was shot out to Jupiter, and at Jupiter it got a gravitational slingshot effect. We looked at that last quarter, that more or less maybe about tripled its speed. And so that gave it enough of an oomph to get out of here. So this is 43.5 needed to escape. You have to multiply that by about nearly 3 to get it to go. And that's what it did out there. Okay, we'll stop there for today. Again, I've got a new formula sheet I'm going to publish here or post today, and I'll probably put it in an announcement or something that you can link to it and print it off. And then I'll get this lecture going there too. So I'll stop recording.